Ultimate stress design method. Ultimate stress design method is used extensively and almost exclusively in many countries for structural design practice. WSD method designs RC section assuming them to be within the elastic limits where stresses are proportional to strains. Large margins or factors of safety are assumed on material strengths to ensure such behavior. It is equally, if not more, important to predict the ultimate strength of RC section so that they can be designed to resist the largest loads anticipated during their design labs. The materials are not expected to remain within their elastic limits at such high stresses. More realistic methods of analysis based on actual inelastic behavior rather than assumed elastic behavior of materials, and on results of extremely extensive experimental research have been performed to predict the, the ultimate strengths. So this is the sample. Uh, Assumption of ultimate stress design method. Number one is stress in reinforcement. Varies linearly with the strain up to the specified yield strength. The stress remain constant beyond this point as strains continue increasing. This implies that the strain hardening still is ignored. Concrete sections are considered to have reached their flexural capacity when they develop 0.002 strain in the extreme compression fiber. Strains in reinforcement and concrete are directly proportional to the distance from neutral axis. This implies that the variation of strains across a section is linear and unknown values can be computed from the known values of them through a linear relationship. Tensile strength of concrete is neglected. Compressive stress distribution of concrete can be represented by the corresponding stress strain relationship for concrete. Limitations of ultimate strength design method are collapse of flexure, compression, shear, and torsion. So, this is the question. A footing 2.15 meter wide by 2.15 meter long and 0.40 meter thick carries square column of 0.45 meter by 0.45 meter on each center. Given effective depth of footing is equal to 0.30 meter concrete, F prime C is equal to 21 MPa, reinforcing steel is equal to 275 MPa. Allowable stresses at ultimate loads for two-way action shear is equal to 1.52 MPa. For wide beam shear is equal to 0.78 MPa. For letter A, based on a two-way action shear, what is the allowable axial load at ultimate condition? Letter B, based on wide beam shear, find the allowable axial load and the ultimate stresses. And letter C, the design moment at ultimate loads at the face at column is 330 kN by kilonewton per meter. How many 16 mm bars are required? This is the following are the solution. First, given the details, the size of footing, the depth, size of column, the FRMC and FY, and so on. Then draw your free body diagram, the dimensions of column. And the following are the solution in the formulas and solutions. And for allowable axial load based on two-way shear, sub 1 is equal to 1764.72 kN, while based on wide beam shear, actual load is 3605.5 kilonewton. Then design moment, mu is equal to 330 kN per meter, or 330 divided by 10 raised to 6 Newton per millimeter. Then formula is AS multiplied by Fy over 0.85 multiplied by Fc multiplied by B. So to find the mu is, and I put the value of the variables, makakuha tayo ng sagot na AS is equal to 8,766.8 square millimeter. Then the number of 16 mm bar, so yung nakuha natin na 8,766.8 over pi over 4 multiplied by 16 squared, 43.6, or equal to 44 bars. That's it. Thank you for listening.